Okay, this week we're going to look at Unit 8, which is vectors. And vectors is a topic that we typically look at. I'm not going to go nearly as in depth as I normally would if we were in class. We're going to stick with the more simple vectors, but it ties right in with the trig that we're using. It's also very helpful if you are going to take physics at any point. So if you have physics in college, or if you have physics through the virtual public schools or something, this might be helpful to you. So I think it's a good topic to at least be introduced to. We're not going to go really in depth with it, but we're going to do the more basic problems. So a vector is a quantity that has both magnitude and direction. The vector you are probably most familiar with would be velocity. Velocity is not the same as speed. Speed only has magnitude, so it's how fast you are going, but it has nothing to do with direction. Velocity includes both magnitude and direction. So your velocity includes how fast you're going, your speed, and the direction that you are going. So velocity is going to have a direction to it. There are other things that we'll look at that can be seen here. A vector is represented geometrically by a directed line segment, which we're going to see here in a minute. The length of that line segment is your magnitude, and if a vector is in standard position, the direction of the vector is the angle between the positive x-axis and the vector. We'll see all that here in a second. Okay, so here is an example of a vector, and that vector is graphed as a directed line segment. It looks like what we would call a ray. It's got an end point here, and then it's got an arrow on the end. However, that arrow indicates the direction that it's going. It's not like a ray in that it goes on forever and ever and ever and ever. So that line has a certain length. It also has an angle right here that is the angle it makes with the x-axis, so that's its direction. So we won't do a lot of drawing vectors to scale, but I just want to do one so you can see an example of that. So if we're asked to sketch a vector that has a magnitude of 3.6 whose direction is 30 degrees. So first I'm just going to draw my x and y axis here. Hopefully that's far enough. And then if I go over here, I hope this has a ruler. No, the one at school does. Let's see. Oh yeah, there we go. And I also need a protractor. If we were actually in school, we would do a little more of this, of drawing this stuff to scale. But given that we're not going to go into great detail with this. But if I wanted to draw a vector that has a magnitude of 3.6 and a direction of 30 degrees, I'd start off with my degrees, so I can see right here that I would have 30 degrees. I'm just going to put me a little mark right there at 30 degrees. And then I'm going to move that protractor out of the way. And then I could go up here and take my ruler. I'm actually going to make that ruler smaller just so it fits. I realize in real life that making a ruler smaller is crazy. That can't do that, or it's no longer the same distance. But this is just for your own visual here. And it's a little hard to get it just right. Right there's pretty good. It starts at the x-axis, it goes through here. So you would want a length of 3.6. So I'm going to choose, I'm actually going to do this right here. I'm going to want this and this, and we want to make it, let's make it green. So my vector here, I just go out here to 3.6. I'm just going to sort of eyeball it here. And so this would be my vector. And so it has a length of 3.6. In this case, it was inches, and 30 degrees. Right here is the angle. So that would be how you would draw a vector there if you were going to draw those by hand. So What we're going to focus mainly on is adding vectors. So vectors, let me make this a little smaller so we can see the whole thing. To add a vector, there's two methods that you can do. The first method is the triangle method, and in the triangle method, this is what we'll do. We'll take, I'm just going to copy and paste these vectors right here. So copy, paste. If I'm adding these two vectors right here together, what you do is you take one of the vectors, not that, there we go, is your starting vector. So we'll let this one right here, actually I'm going to let this one right here be my starting vector. And then we take the second vector and we put the end point of that vector, oh come on, having trouble with it here, I don't want to actually, there we go, just want to move it. Well, sorry guys. There we go. We're going to put the endpoint of that vector right there at the arrow of the first vector. And so your resultant vector, the vector you get when you add these two together, is going to be this vector right here. I'm going to make it red. Not that one. This vector right here that goes from our beginning end to the arrow on the end. And so that would be that. Okay. The other method that you can use to add vectors is called the parallelogram method. And when I do the more difficult vectors, that's usually what I use. We're not going to do the really difficult. We might only do like one of the really difficult vectors. So we might actually not use it as much as I usually do. Let's see if I can. And I actually need to copy and paste this twice here. Alright, so what we would do is we would have both of the vectors share the same endpoint here. And then we would make a parallelogram out of those vectors. So I could I'll take this one so it'll be perfect right here. And this one right here. And so notice that we have the two endpoints are together, and then the two arrows are together here. And so our resultant vector for this one is going to be from the common endpoint to the common arrows. Now, if you'll look, the method that you use really doesn't matter, because right here, this vector is pointing in the exact same direction, as the same length as this vector down here. In fact, if you look at this, just the right hand side of what you've got here, it's the same as this triangle method here. So both methods work fine. It's just really whichever one you prefer. I'll use a little bit of both probably for these. For the easier ones, it's really doesn't matter. They're both pretty simple. So let's do a problem. So A has a magnitude of 3 in a direction of 90 degrees, and B has a magnitude of 4 in a direction of 180 degrees. So we need to find A plus B, or we're finding C. C equals A plus B, and so we're finding C. Now, these little arrows that I've drawn in here over the A, that's the symbol that's used for vector. You can't type it on this particular program, so it doesn't look very good, but it's kind of like half of an arrow. It's kind of like an arrow that's been cut in half. So if we draw our X and our Y axis here, let's go back. Let's make it just black again. So if we draw our X and Y axis here, vector A has a magnitude of 3 in a direction of 90 degrees. So I'm going to go back to a vector, and let's make this one blue. And so 90 degrees, if you're thinking unit circle, let's go back into, it's just straight up right here, and I'm not actually going to measure this or draw it to scale. That would be 3 right there. We're going to call that 3. And then Vector B has a magnitude of 4 and a direction of 180 degrees. So I'm going to draw that in, and let's use red for that one. And so 180 degrees would be to the left here, and I'm going to make it a little bit longer than the other vector here. So let's label this stuff. We've got 3 right here. We've got 4 right here. Now, we know that 90 degrees and 180 degrees are perpendicular to each other there. So what we're going to do is we're just going to make this a parallel. Oh, gosh, that's ugly. Let me just use the dotted lines here. So I'm just going to make a vertical line up here, a horizontal line here, to make this a parallelogram. Now, what students typically do wrong with vectors is they draw a line right across here. They connect those two arrows together. That is not what you are going to do for vectors. So for vectors, you are going to start at the common endpoint right here and go to the opposite corner. So you should have, here I'll make that a little more profound, you should have a dot right here and an arrow on the end. So this is your resultant vector here. So what we end up with, we have this direction. We also have the length here. Now I know this is 3. I know this is 4. And since this is a right angle, this makes it really easy to find hypotenuse there. So you're just doing 3 squared plus 4 squared equals 5 squared. Well, I've already done that. This side right here is 5. I should have put an X right there, but a 3, 4, 5 triangle is a really common one that we know. So X is going to equal 5 whenever you solve the Pythagorean theorem. So that is your magnitude. So your magnitude is 5. The direction is going to be the angle right here. And so I know this part of the angle would be 90 degrees, but I need to find this angle right here. This little angle right here, so I can know what that direction would be. So I'm going to call that theta for right now. And so if I'm looking at theta, I know all the sides of the triangle, so I could pick any of the trig functions, sine, cosine, tangent. It does not matter which one you pick. Let's just pick sine of theta, and sine is the opposite over the hypotenuse. And so if theta is the angle that we see right here, then 4 right here, this is my opposite side. It's across from theta. And then the hypotenuse is the side that we just found, the longest side of that triangle. So sine of theta would equal 4 over 5. And what we want to do here is we want to find the angle theta. So we have to do sine inverse of 4 over 5. Sine inverse is the function that gets rid of sine. So over here it just cancels it. And sine inverse over here. So in Desmos, you can just type it in, sine to the -1 of 4 over 5, like that. Oops. And I think we are in radian. Desmos defaults to radian, so let's go to degrees here, and we get 53.130. So theta equals 53.130 degrees. But to get this full angle right here, think like unit circle angles, we're going to add 90 to that. So if we add 90 to that, we'll get 143.130 degrees. And that is my direction. Okay. So that's a very, what I would call a naked problem. You don't have any context of anything that's happened there. So let's look at one that has some context here, because this is really applicable. The questions we're going to look at are going to be sort of oversimplified just to make them ones that we can do, but they are very applicable in a lot of different situations. So a wind blowing can be represented by a vector. The vector has an eastward component and a northward component. If the eastward component has a magnitude of 20 miles per hour and the northward component has a magnitude of 8 miles per hour, what direction is the wind blowing? Okay, so in this case, we know we have two vectors. We have a north vector and east vector, and we want to know the direction that the vector will go whenever those two combine. So you can kind of think of like a fan blowing north at 20 miles per hour and another one blowing east at 8 miles per hour, and what will happen there. So let's draw this, and we'll make this a little bit bigger. Okay. All right. All right. So the vector that has an eastward, let's see, the eastward component has a magnitude of 20. So going to the east right here, we have a magnitude of 20. We have a northward component and a magnitude of 8 miles per hour. Now I'm going to use a triangle method for this just once because I want you to see how that'll work. So instead of putting my vector over here where they have the same endpoint, I'm going to go ahead and put the second vector. It's going to begin at the end of the first vector. So you can do it this way if you would like, or you can just use the parallelogram method. So this is 20 miles per hour, and this is 8 miles per hour. And so the resultant vector will go, oh wait, no, change my colors. Resultant vector will go from the beginning of the first vector to the end of the second, and it'll be this red vector that we have right here. So it does not ask us about the magnitude. Now, if we needed to know magnitude, we just do 20 squared plus 8 squared, take the square root, do Pythagorean theorem there, and get our magnitude. But the question only asked about the direction the wind was blowing. So this is what we want to find. We want to find this angle right here, and we'll call it theta. So we want to find that angle, and that angle, what we can do when we get that angle is we can describe the direction of the wind, and I'll show you how whenever we get the angle. So I only have two sides. I could find the third one if I want, but this side right here is my opposite side, and this side is my adjacent side. So opposite and adjacent, that's tangent. Tangent of theta equals opposite over adjacent. So if I say tangent of theta equals 8 over 20, then I'm just going to have to do inverse tangent to get rid of the tangent here. So over here I'm going to do inverse tangent, and if you don't like typing that in or you're having trouble with that, the inverse trig functions are over here under functions, inverse tangent of 8 over 20. And it gives me 21.801 degrees. Okay, so that's my angle right here. Now, whenever we're talking about direction, we need to know 21.81 degrees from what. So in this case, what we would say is that's 21.81 degrees north of east. Now, sometimes this can be a little bit confusing. Whatever direction you're going of, that is the main direction right here. So, like, if you look at that angle, it actually touches east right there. So since it actually touches east, you are going to, that's the one that's going to go second. And then you're going from east, you're going up to the north, 21.801 degrees. Now, this is one of the answers that could be given for this problem, but depending on how you set it up, you may have set it up using a parallelogram model. And if you did that, then you might have, let's see, I'll move this one over here. If you did a parallelogram model, you might have, instead of finding this angle, you may have found this angle right here. All right, and so we know just from geometry that 90 minus 21.801 is going to give us this angle. This angle right here is 68.199. And so, this is a correct answer, but we could also say that this is 68.199 degrees east of north. There, and we might do a little extra practice with that. But those are both correct answers. You don't have to give both answers, just one is fine. I think probably the smaller angle is typically the one that's used, but not always. So those are both possible answers for that problem. Okay, let's continue on. This is another good problem. An airplane is flying due east at a velocity of 450 miles per hour. The wind is blowing out of the north at 20 miles per hour. In what direction is the plane traveling, and what is the magnitude of the plane's resultant velocity? So, here I was saying these are really applicable situations. This is something that very well could happen. They are kind of sanitized so that they're a little bit easier for us to deal with. For example, the plane probably isn't always flying perfectly east. It might be flying 20 degrees north of east, like we saw in the last problem. And also the wind might not be perfectly blowing out of the north. It might be at a certain angle. So that can make the problems more difficult. And normally in class we would deal with those some as well. But since we are trying to learn from home, we're just going to do the more basic problems. So if you have an airplane and it is flying, let's see, what direction was it? It is flying 450 miles per hour due east. So it is flying to the east here. I'm going to make this a pretty long vector because 450 is pretty big. The airplane and the wind is blowing. Be really careful right here because this says out of the north. So if something is coming out of the north, it means it's coming from the north. It's going towards the south. So whenever you draw in this little vector right here, this vector of 20, it's got to go towards the south. I'm going to use parallelogram method again here. If you wanted to, you could use triangle if you want. So for parallelogram method, I'm just going to make myself a parallelogram. So I'm going to draw this line on out and this line on down right here, and then the resultant vector, let's go red here, is going to go from the common endpoint to the opposite corner over here. And let me label this a little bit. This was 450 miles per hour, and this side was 20 miles per hour. And so this side right here, we want to know that length, and then we also want to know the direction. So for our direction, we could find either one of these angles right here. I typically just like to find the smaller angle, so I'm going to go for this angle right here, but you could use either one. I'm going to call that theta. So let's do direction first. If this side over here is 20, then this side is 20. So I'm going to put a 20 right here. So it says, in what direction is the plane traveling? And so we have, again, this is my opposite side right here. And this is my adjacent side. It's like we're ignoring this bottom triangle. We're only looking at this one over here. And so that tells me tangent of theta would equal 20 over 450. And if we do inverse tangent here, let me just go up here, 20 over 450, we're going to get 2.544, or 545 if we round, so 2.545 degrees. Now, we need to put a direction with this because it's 2.545 degrees from what? And so the main direction, if you look at your angle, this angle right here, theta, that we have marked, sorry, this angle that we have marked, it actually touches the east. So, and then it's going below the east, so it's south of east right here. So whichever one it's actually touching, the side that it actually touches, because right here would be east, over here would be south, we would say 2.545 degrees east of, oh, I said that backwards, sorry, right, the opposite of what I just said a minute ago, south of east, right here. So main direction is east, but you're going 2.545 degrees south of that. So that wind is knocking that plane off course by 2.545 degrees. It's not a huge difference, but if you're traveling a long distance, that's something that's got to be corrected for. For part B, we want the magnitude. Well, for that, we just need the length right here, and this is a right triangle because south and east are perpendicular to each other. So we're just going to do Pythagorean theorem here. 20 squared plus 450 squared equals x squared. And so we'll do 20 squared plus 450 squared. And we get this, and then we're going to take the square root of it. Oh, wait. Oops. So we get 450.444. So 450.444 miles per hour. So it does not change the actual speed of the plane very much. It makes it go like 0.444 miles per hour faster than it was going, but this angle is what would really be concerning if you are operating the airplane, or especially if you're developing all of the sensors and mechanics and stuff that fly the airplane, because there's a lot of computer stuff involved in that. So here's another example that you'll see. Okay, this is another example that, especially if you take physics, you're likely to see a lot in much more depth than what we're looking at here. But you have a rope is pulling an object straight upward with a force of 50 newtons. Another rope is pulling an object towards the right with a force of 30 newtons. Find the magnitude and direction of the resultant force of the object. So let's just draw in here. We've got the ground is right here. And let's just find a picture of, let's see if it's got something. Got 23 pictures of boxes. Let's find one that we like. Okay, here's our cardboard box. Let's make it very small. So we got our little cardboard box right here. Oh. Let's set it on the ground, and we're going to attach 2 strings to this box, and we've got one that goes upwards with a force of, let's make that a vector. We've got one that goes upwards with a force of 50 newtons. We also have one that goes to the right with a force of 30 newtons. So if you look at this, the rope that's pulling the object upward has more force than the one that's pulling it to the right. So if you're just thinking off the top of your head, the vector should go more north or more upwards than it should to the right. Maybe something like this. It's actually going to be about like that. But it would not look like this. So to know exactly where it goes, we can make ourselves a parallelogram. And so we would just draw a horizontal line here and a vertical line here. And then our resultant vector, let's make it red, would go from the box up here to the corner. And so this is the direction that the box would actually travel when you have both of those ropes pulling on it. You could think of maybe a crane or something when you're trying to get something in place perfectly. You might have the crane pulling it upward, but then you also might have another rope to pull it into place where you need it. And so this is 50 newtons, and this is 30 newtons, which also means this would be 30, and this would be 50. And so we are supposed to find the resultant force on the object and the direction. So the force, we're just going to do Pythagorean theorem here. So we'll have 30 squared plus 50 squared is going to equal x squared. And so if you do that over here, 30 squared plus 50 squared is 3,400. If you take the square root of it, you're going to get 58.30, well, let's go 310. So 58.310 newtons here. So that would be the force that we have in this direction. That's the 58.310. That's the force of that vector right there. We also need the direction. I'm going to put the direction right here. You technically could put it right here. You don't really need to put north or south on this one because north or south don't really apply in this situation. We're not talking about north-south or anything. So typically we'll give the angle to the horizontal, which would be this angle right here. And so again, this is opposite right here and adjacent. So we use tangent. Tangent of theta equals 50 over 30, because right here this is the opposite side across from the angle, and here's the adjacent side. And if we do inverse tangent of 50 over 30, we're going to get 59.036 to the horizontal. And so that will be your answer for that problem. I'm not going to do some of these other problems that get into things that are a little bit more difficult. You will have some work to do with these problems in some different situations. If you have trouble, let me know. And then on Thursday we will meet. On Friday, you guys will have a test, even though nothing's really a test anymore, that'll have some law of sines, some law of cosines, and some vectors on it. Oh, sorry guys, I'm back. I forgot to do this last problem that you need to know how to do. So, you thought you were done, but you're not. So, a wind is blowing at 45 miles per hour. The wind is blowing in a direction 30 degrees south of west. Find the westward and southward components of the wind. So, in this case, I'm just going to go ahead and draw the axes in. We are south and west, so the wind is blowing 45 miles per hour in a direction 30 degrees south of west. So right here is west, right here is south. West is our main direction, and our wind is blowing 30 degrees to the south of that. So you would have a vector that would look something like this, and this right here would be 30 degrees. And so what we want to know is we want to know the two components that make that up. So what we're looking for, if you think about doing this problem, if you had both components, let me change some colors here, you would have, this would have a westward component, and then it would also have a southward component, like so. So we want to find both of those. So what you're going to do for this is going to be a little different than what we did on the other problems. I'm just going to call, let's see, this part right here we know is 45, and I'm going to call this part right here, I'm going to call this W because it's our westward component, and I'm going to call this one S because it's our southward component. And so let's look for S first. Ooh, I don't know where that came from. So S is the side that's opposite of that 30-degree angle, and we know 45 is the hypotenuse. Whenever we have opposite and hypotenuse, we're going to use sine. So, or we could use law of sines here if you want, if you prefer law of sines. So we're going to say, for this, sine of 30 degrees equals the opposite, which we don't know, that's S, over 45. And to solve for that S right there, we just have to multiply both sides by 45. And so if we do that, oh, where'd my, I think I closed my Desmos tab. Oh, let's make it small. Sorry, guys. Okay, so if we do 45 sine 30, and we need to go back over here and change this to degrees, we get 22.5. So southward has a magnitude of 22.5 miles per hour. We would also need to find westward. Westward here is the adjacent side over here. So for adjacent, you could use tangent, but I'm going to use cosine because I know hypotenuse is 45 and I don't have to round for that. So adjacent over hypotenuse is cosine. So I'll say cosine of 30 degrees equals the adjacent side, which is my westward component, over my hypotenuse, which is 45 right here. And so we would multiply both sides by 45. And whenever we do that, we're going to have 45 cosine of 30. And that's going to give us 38.971 miles per hour for our westward component. So that breaks down that that wind into a southward and a westward component. This could be important, like if you had a westward facing wall or something and the wind was blowing against it, you would be concerned with this speed right here, so that the southward component wouldn't really affect that, but the westward would. So that is the last type of problem that you might see on your assignment. I'm done for real now.